Hi everyone, I'm Harman. In this presentation, I'm going to talk about the work that I did with my collaborators at Microsoft Research. Our goal was to find opportune times to recommend task transitions and breaks to people when they were stuck in unhappy or unproductive states at work. Let me begin with explaining our motivation for this work. Multitasking has become a common characteristic of knowledge work. Information workers are constantly switching between tasks and juggling multiple deadlines, managing an ecosystem of devices with information spread across these, and managing both in-person and online interactions, both work-related or social. While all of these form necessary sources of context for helping people be more productive, we are missing a crucial piece with this productivity-centric perspective. Productivity and well-being are inextricably linked. Imagine this line as representing passage of time. We know that there has been an increase in multitasking due to managing multiple deadlines, information sources, and device ecosystems. Managing all of these things at once often leads to an increase in stress. Being stressed or unhappy at work, in turn, hurts productivity even further. With productivity loss, work piles on even more, increasing the number of conflicting deadlines, and the cycle continues. The question then becomes, how do we break out of the cyclical process of being unhappy, stressed, and not productive at work? We can think of a potential solution space by finding ways to recommend state-changing actions when someone is unhappy or unproductive at work. This can be in the form of a break or even transitioning from one task to another. However, the challenge here is that these state-changing actions must be recommended at the right time, or else they become another source of distraction rather than helping improve productivity and well-being at work. Therefore, the primary research question we tackle in this work is, can we identify opportune times for people to transition between tasks or take breaks during their workday? In short, the answer is yes. But to elaborate on our contributions, we contribute an approach that optimizes both happiness and productivity by using contextual emotion and activity signals along with daily task lists and productivity reports. In a field study, our approach provides opportune time recommendations of transition and breaks with 86% and 77% accuracy, respectively. Interaction data, such as mouse and keyboard use, windows and tab switches, task information, for example, urgency, difficulty, anticipated completion time, emotion, and physical movement, emerged as the most important features for predicting a jointly optimized happiness and productivity value. We answered our research questions via a two-phase study setup. In phase one, we focused on model development and followed a pretty standard model development pipeline. Phase two takes these models from phase one and seeks to validate them via a field study. Phase one is split into 4 steps. First, we introduce a tool called FlowZone that collects all the necessary data. We use this tool to collect data over the course of 3 weeks. Then we pre-process this data to align all the different signals being collected from users, and finally, test different models for our prediction task. I'll go over the specifics of each step in this process over the next few slides. Our tool FlowZone remains active in the background during the entirety of someone's workday. The first ask for data collection from the user is at the beginning of their workday when they first log in, and the tool asks them to add their task list for the day. It also asks for some information for each of these tasks, such as task type, urgency, anticipated completion time. After this, the tool checks in with the user at hourly intervals to ask about task progress as well as how they're feeling. Throughout their workday, an emotion and activity logging software runs in the background, which records users' emotional state, as represented by their facial expressions, and the activities being performed on their workstation. I want to note here that while we do process people's facial expressions to predict their emotional state, this is done in real time to avoid storing any data related to a person's facial features. Our tool FlowZone, along with the emotion and activity logging software, gives us the following feature categories and specific features. We obtain emotion, heart rate, physical movement, interaction data, and any actions being taken by the user via the logging software. We record timestamps to get time and day values. FlowZone asks people for task information for every new task in their task list for the day. This includes information about task type, its urgency, difficulty, and anticipated completion time. And finally, we calculate our main output variable, a joint expected value between task progress, affect, and an interaction variable between the two based on the data collected in the hourly self-reports. We collected data from 25 participants over the course of 3 weeks. There are several details about how each of the features we collected were carefully pre-processed. Please refer to the paper for these. I do want to note details about the underlying temporal pattern of our data and how we handled that. The data collected by the logging software is at a microsecond level granularity, making it a time series. The self-reported data collected from the user is at hourly intervals. Any more than this would be a distraction, as shown by prior work. The hourly self-reports are thus the limiting factor. We have 62 self-reports per participant on average, and thus 62 data points where we have all the data signals. To model this data in its natural form, a time series, we upsample the hourly interval data and downsample the microsecond level data. To upsample, we applied growth and decay functions to the values at every hour. We used these functions to determine values at each point between two hourly values. We tested different time samples for upsampling, ranging from every minute to every 30 minutes, and different growth and decay functions. These were all optimized as hyperparameters. We aggregated the microsecond level data to match the same time sample. We further validated the simulated time series dataset by comparing its results to the original dataset for a subset of our models that can work with such small sample size. We built ARIMAX models for our data since it represents a time series. ARIMAX models are able to account for historical data in a time series as they try to forecast the values of data points in the future. These models give us significant estimates for several features per participant. This table shows the number of participants for each feature category who had a significant estimate for one of the features in that category. As you can see, past actions, whether you have transitioned to a new task or taken a break or neither, have a significant impact on future predictions of which action to take. Task information, interaction data, emotion, all seem to be important for a large number of participants. ARIMAX models are the best way to model our time series data. However, their computation time is 15 minutes on average, which makes them infeasible for use in a real-time recommendation setting. Since ultimately, our goal was to recommend transitions or breaks to people in real time, we tried to model our data using other, less computationally expensive regression models, and relied on our ARIMAX results to validate the choice of model in the end. Through this process, we found random forest regression models to have the best performance and match with our ARIMAX models. We first tried a general random forest regression model using data from all participants. This performed moderately well in terms of R-squared and adjusted R-squared values. It explained 20% variance in our data. We also built personalized models, which had a moderate to good performance depending on the participant, and similarly, cluster-based models, which also performed well. For the cluster-based models, the clusters were based on job roles, which included software engineers, data scientists, designers, etc. We built models at these 3 levels of granularity to test if we could account for the cold start problem of not having enough data for personalized models for everyone from the get-go. Now you might ask, why build the personalized models at all if the general and cluster-based models perform reasonably well? Upon evaluating the specific feature importances for each of these types of models, we found there to be a significant difference in the general or cluster-based models compared to the personalized ones. This led us to believe that while these aggregate models can be helpful to begin with, eventually having personalized models is the only way to represent an individual's workplace productivity and affect in the most accurate way. For random forest regression models, the feature importances across categories sum up to 1. Here, the important features are interaction data, task information, emotion, physical movement, overall quite similar to our ARIMAX results. In fact, if we directly compare the importance order for the 2 types of models, most of the important features remain the same. This again validates the use of random forest regression models in this time series setting. One major difference between these two models is in the action class. Actions can be continue, transition, or break. It makes sense that action is extremely important in ARIMAX models, whereas not so much in the random forest regression models. ARIMAX models consider historical data when making future predictions. Therefore, having taken a break or a recent transition would be factored in when forecasting. Random forest regression models do not have this kind of historical nuance. Next up, we have Phase 2. In Phase 2, we update Flowzone to provide real-time recommendations for the participants from Phase 1. We collect their feedback on the timing of these recommendations and evaluate Flowzone based on the results of this field step. We add front-end and back-end components to Flowzone to be able to provide real-time recommendations. We rely on the same data collection tool, our initial version of Flowzone. This tool sends data to a model-based backend every t minutes, where t is a personalized variable for each participant, a hyperparameter that we optimized for in Phase 1. The model-based backend takes this new input data and uses the models from Phase 1 to make a recommendation. If the recommendation is break or transition, we show a new form to the user that describes the recommendation and asks for their feedback on its timing. If the recommendation is continue, we do nothing. We split our participants into two conditions, a control condition and our model-based recommendation condition. The control condition recommends an action every 30 minutes, whereas the model condition recommends an action every t minutes, where t is a hyperparameter optimized for each individual. The control condition recommendations are based on heuristics-based probabilities, a sixth each for transition and break and 2/3 for continue, whereas model condition recommendations are based on predictions from the personalized random forest regression models. Participants used our updated version of Flowzone and provided feedback on these recommendations for 3 days. We also asked them to fill out a post-study survey about their experiences with Flowzone. When we look at the results, as expected, the control condition provides a similar number of transition and break recommendations throughout the day, whereas the model condition recommends more breaks than transitions. We started with the goal of recommending transitions and breaks at opportune times. Based on the feedback from our participants, we find that our models have this opportune timing for 85.7% of the transition recommendations and 77% of break recommendations on average. These numbers are higher than those of the control condition recommendations. One interesting thing to note here is the difference in frequency of transition and break recommendations in our model condition. It appears that the models are able to distinguish between task switching and breaks as two potential ways of changing from unproductive or unhappy states. Please see the paper for an in-depth discussion of the survey results from Phase 2. Our unique setup of productivity and affect signals and their use in a real-time transition and break recommender provides helpful insights for future work in this space. We found that frequency and timing of recommendations are indeed the primary metrics that people use to evaluate recommendations of breaks and transitions at work. Our goal of optimizing for these opportune times was also reciprocated by the participants as one of the main desired features for tools like Flowzone. We also found evidence in favor of our motivating happy productive worker hypothesis. Personalized models that optimize both productivity and positive affect perform better on both metrics compared to control. Based on their feedback, we noted that people wanted to always have control over what went into their recommendations and that this was contextual. For example, someone might choose to weigh well-being above productivity or vice versa, depending on the situation or their mood. It's entirely personalized. Finally, we were excited to see the many future work opportunities that can build on this work, including understanding and capturing all relevant context for making these kinds of recommendations. Thank you for listening to this presentation. If you have any questions, please feel free to contact me or any of the authors.